Okay, so you guys will remember that we can do a bunch of different things with our equilibrium expression. So if we know one part, we can find a bunch of other things. So in our last examples, we were given the equilibrium concentrations, but we are not always given those values. Sometimes we only know what we put into the reaction, and then we have to use our stoichiometry skills to find kind of those equilibrium concentrations and ultimately a Kc value. So let's try a few of those. So we are going to be given some different information, and we're going to put it into an ICE table. So we have looked at an ICE table when we talked about gas laws, but it means initially, change, and add equilibrium. And we're going to fill in what we know, and then we'll fill the rest of it in using our stoichiometry skills. So a closed system initially containing 1 times 10 to the negative third molar H2. So this is the major difference. It is initially containing that amount. That is not the equilibrium amount. Okay, so watch for that wording. It also has 2 times 10 to the negative third molar of the I2 at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows us that the concentration of HI is 1.87 times 10 to the negative third. So now this second part is of the equilibrium mixture. So we're given some initial concentrations and we're given an equilibrium concentration. Okay, so this ultimately is asking us to calculate Kc for this reaction. So you guys, this is a typo here. This should be gas because we want it to be included in the expression. So I'm going to set up my ICE table, and the way that I set up an ICE table, I put my reaction up above, and then I create a column for each of the things that are going to be included in the reaction. The first thing that I'm going to do is kind of put in what I know, and then I'm going to write the equilibrium constant expression. So according to my scenario, we are starting with 1.00 times 10 to the negative third molar of the H2, 2.00, and again, that should be gas, times 10 to the negative third molar. And then if it doesn't say we put any in there, we're going to assume that we started with none of the product, okay? We were also told that at equilibrium, we had 1.87 times 10 to the negative third molar of my HI. So ultimately, we're looking for Kc. So Kc, the equilibrium expression, is the concentration of HI. That's going to be squared because it's got a coefficient of 2. H2, and then I2. And you guys, this Kc value can only be calculated at equilibrium, which means that I need all of these values in order to calculate Kc. I can't combine initial and equilibrium values. So what I'm going to do now is use stoichiometry to make some guesses about what these changes look like. So I know that if I started with 0 HI and I ended up with 1.87 times 10 to the negative third, that I had to have added 1.87 times 10 to the negative third during this reaction, which means that I can figure out the other parts using stoichiometric coefficients. So in this equation, there's 1 hydrogen for every 1 iodine and every 2 of the HIs. So that means that it's twice as much. So in order to find how much of the reactants were lost, I'm going to take half of my product, 1.87, e to the negative third, and I'm going to divide it by 2. Again, I'm dividing it by 2 because my product is twice as much as my reactants. So that ends up being 9.35 times 10 to the negative fourth. And since these are 1 to 1, this is also 9.35 times 10 to the negative fourth. Okay, and they're reactants, so we're losing them. So now I'm going to subtract. So 1 times 10 to the negative third minus 9.35 times 10 to the negative fourth is 6.5 times 10 to the negative fifth. And I'm going to do the same thing on this one. I'm going to take the 2 times 10 to the negative third minus 9.35 times 10 to the negative fourth, and I get 1.065 times 10 to the negative third. Now that I have all of those equilibrium values, I can go ahead and just plug them in. So I'm going to take 1.87 times 10 to the negative third squared divided by 6.5 times 10 to the negative fifth times 1.065 times 10 to the negative third. And I find that my Kc value for this one is 51. Okay. So when I have a value greater than 1, I know that this is product favored. Okay, let's look at another example where we're given slightly different information. So in this one, it says a mixture of 0.10 moles of NO, 0.50 moles of H2, and 0.10 moles of H2O is placed in a 1 liter vessel at 300 K. The following equilibrium is established, and at equilibrium, we're given this value. So the values up at the top are initially because they're being placed in the 1 liter vessel. So that's what we're putting in the vessel. And then at equilibrium, we have some information as well. So we're going to set up an ice table. I've got each of the parts of my reaction in the ice table. And then I'm going to plug in what I know. So 0.10. Let's see. Oh, wait. So it's placed in a 1 liter. So I'm given moles values. So I'm given 0.10 mole in a 1 liter. So that's not going to change it at all. So I can use those mole values as molarities. Let's see. I've got 0.50 of the H2 and I have 0.10 of the H2O. So I am told nothing about the N2, so I'm going to assume I didn't start with any of that. Okay. So then it says at equilibrium, my NO is 0.062. So I need to kind of determine what was my change. So I'm going to take 0.10 minus the 0.062, and that tells me that I lost 0.038 molar during this process. So now to determine what the other change pieces are, I need to look at the stoichiometry. So my NO, my H2, and my H2O all have the same coefficient, which means their changes are going to be the same. So I lost reactant and I gained that much product. Okay, now to find my N2, its coefficient is just 1. So it's going to be half of that 0.038 value for my N2. Because it's only 1, it's not 2. 2, that gives me 0.019. And since it's a product, it's going to be gained in this case. Okay, so I'm going to do my math. 0.50 minus 0.038. 462. This will be 0.019, and then 0.10 plus 0.038 is 0.138. Okay, so now I know all of my equilibrium values, and I can put it into my Kc expression. So it's going to be the concentration of my products, so N2, and then H2O squared, since it has a coefficient of 2. Over NO squared and H2 squared. Okay, so plug in my values, 0.019, 0.138 squared, 0.062 squared, and 0.462 squared. Okay, so when I do that, again, be careful with how you type this into your calculator. So I want you guys to try it. Whatever calculator you're going to be using for the AP test, use that one now so you can make sure you know how to work it. When I type it in, I'm going to do the 0.138 squared first, and then times the 0.019. And then I'm going to divide it, and I'm going to use parentheses. So I'm going to do parenthesis 0.062 squared times 0.462 squared, close my parentheses, and I get a Kc value of 0.441. So that tells me that in this case, I am reactant favored because I am less than 1. Okay, so you guys, those two problems were fairly straightforward because we were given one of the equilibrium values. There is also a possibility, though, that we would have to do a problem where we are not given an equilibrium value. We are given the Kc value instead. So that makes it a little bit more challenging to find that chain piece. Okay, so let's look at one example like that. So if 0.20 moles of SO2Cl2 and 0.1 moles of Cl2 are placed in a reaction vessel initially, what will be the equilibrium concentration of each substance? Okay, so now we're looking for the equilibrium concentrations and we're given this Kc value. Okay, so let's plug in what we know. So again, I set up my ice table. And I know that I'm starting with 0.020 moles. I'm going to assume that it's a 1 liter vessel. So I'm just going to do 0.020 and 0.10 of that one. And so I'm going to assume, because we didn't say anything about it, SO2 is 0. So here is the problem. That's all that I'm given. So I know that my Kc is equal to the concentration of my products over the concentration of my reactants. And I know that that is 0.078. That's all that I know. So what I'm going to do is make some assumptions. I'm going to use some of my algebra and some of my stoichiometry. So I'm going to say, okay, if I'm starting with some reactant, I'm going to lose some amount of that reactant because it's going to start to react. And what I know from math is that if I know something is going to be there, but I don't know the value, I can give it a letter, and that letter is X. So I'm going to say, okay, SO2Cl2, it's going to lose X. So I'm just going to say minus X. Now here's where stoichiometry comes into play. If our coefficients are all the same, like they are, I know that if I lose X in the reactants, I have to gain X in the products. So at equilibrium, the concentration of my SO2Cl2 is going to be 0.20 minus X. The SO2 is going to be just X, and the Cl2 is going to be 0.10 plus X. Because those are my equilibrium values, that's what I'm going to plug into my problem. Okay, so my Cl2 is going to be 0.10 plus X. Let me use parentheses there instead of brackets. Okay, and my SO2 is X. And then on the bottom, my SO2Cl2 is 0.20 minus X. Okay, so I need to solve for X. So first, I am going to bring my denominator to the top. So I'm going to do 0.20 minus X, which cancels that off, and then times 20 minus X. Okay, so anytime I have a number outside of parentheses, I need to distribute that in. So I'm going to take 0.078 times 0.20, so I get 0.0156, and then minus 0.078x. And then I'm going to do the same thing on the other side. I'm going to distribute that x in. So 0.10x plus x squared. Now, what I'm going to realize here is that I have an x and an x squared. And some of you may recognize this as a quadratic equation. So I want to give you one example with a quadratic equation. I will not ask you to do this on a test, and with the change in our free response questions for the AP exam, you will not have to do a quadratic example on the AP test either, because they said that just a simple calculator will work. You don't even need a graphing calculator for this year's test. So I want to give you an example. I want to show you a difficult one, but I won't ask you to do this difficult of one on your own. So the quadratic equation is set up as ax squared plus bx plus c, a number, is equal to 0. So I'm going to rearrange to this format, and then I'm just going to use an online quadratic equation solver and plug those values in. If you just Google it, you can. Mathisfun.com has one. So I'm going to get this x on the other side. So I'm going to add 0.078x. And that gives me... I'm going to, let's see, 0.0156 is equal to 0.178x plus x squared. And then to get to that format, I also need to subtract my 0.0156 from both sides. So I end up with 0 equals, I'm going to put it in the correct format. So I'm going to do x squared plus 0.178x minus 0.0156. And like I said, I'm just going to plug this in. And when you solve a quadratic equation, you get a positive and a negative root or value. Since we're looking at concentration, this needs to be a positive value. So in this case, x is going to be 0.064 molar. Okay? So now that is not actually the end of this problem, because the question was, what are the equilibrium concentrations? And so we got to do one more little step here. We're going to put that x back up here. So we're going to take 0.20 minus the 0.064, and we're going to get 0.136. Since this is just x, it's going to be 0.064. And then this one, 0.10 plus 0.064, is going to be 0.164. Okay. So you guys, that is the most difficult of those problems. You have 2 practice to complete. There's going to be one where you're given an equilibrium product value, and there's going to be one where you're not, but it won't end in the quadratic formula. You'll be able to solve for x just on your own. Let me know if you have any questions. I am having a session tonight at 3 p.m., so feel free to drop in. I'll probably go over both of the practice problems from today's homework. So give them a try, and then you can come check your answers later.